Hi everyone, this lesson for calculus is about differentiation, and I'm going to be introducing you to the tangent line problem. First, a question. What does it mean when we say a line is tangent to a curve at a point? The answer? We'll get to that later. But first, think back to geometry class. Consider a circle. Oh look, there's one. Here's a circle and its radius from the center to this particular point on the circle. Let's draw a tangent line to that point, also known as the point of tangency. Recall, you learned in geometry that a tangent line is a line that is perpendicular to the radius of the circle. Ooh, tangent line. Now, consider another point on the circle. If we connect the 2 points together to form a new line, this is called the secant line. Let's talk about the difference between secant lines and tangent lines. A secant line is a line that passes through 2 points on a curve, while a tangent line is a line that passes through 1 point on a curve. More specifically, it must be perpendicular to the radius of the circle that contains the point of tangency. How does this help us in calculus? Well, the slope of the secant line is something we call the average rate of change. The slope of the tangent line is the instantaneous rate of change at a particular point. Awesome. Wait, what does that mean? Well, think about when you're driving a car. We can say, on average, how fast you were driving during your trip based on how long it took you to arrive at your destination and how many miles away the destination was from your starting point. If it took you, for example, an hour to drive 45 miles, we can say you drove at an average rate of 45 miles per hour. Were you driving 45 miles per hour the entire time from start to finish? No, I'm confident that you were probably driving at a slower or a faster rate at certain points throughout the trip. You must have at some point driven a rate of 30 miles per hour. Using calculus and the slopes of tangent lines, we can figure out the exact instant in the time that you were driving 30 miles per hour. Okay, now I'm just going off on a tangent. Let's get back to it. Let's practice drawing some tangent lines to curves. Consider this curve. Suppose I want to draw tangent lines to each of these points I've indicated on the curve. Pause the video. Sketch the curve on your paper and try to draw tangent lines yourself at each of these points. Here are the tangent lines. Do yours look like mine? If you struggle with visualizing this, let's go back to our geometry lesson. That a tangent line to a point on a circle is simply the line perpendicular to the radius of the circle. So I need a circle. Great. Suppose the point on the curve is also a point on this circle. Let's draw the radius to that point. Now, can you imagine how to draw the line perpendicular to that radius? Awesome. There's the line tangent to the curve at that point. Imagine rolling this ball or wheel along this entire curve until we hit each and every point of interest. We can do just the very same thing. Draw a tangent line, imagining it like it's perpendicular to the radius of each circle. Cool, right? Now you'll be a pro at sketching tangent lines. Let's look at this example. Here's a curve. Let's label some of these points. Suppose we want to find the average rate of change between points B and D. Translation? You're just being asked to find the slope. Well, that's some easy Algebra 1 business right there. Simply calculate the change in y divided by the change in x. You remember hearing this as rise over run. We're going to be calling that delta y over delta x. The rate of change here is 8/5, or 8 over 5. Now, suppose we're asked to find the slope of the line tangent to point D. This is the rate of change at that instant D. How do we do this? To answer that question, let's consider a secant line in a curve. I have labeled an x value c, and the next x value just c plus delta x. Remember, delta x means the change or distance between the two x values. My corresponding outputs for these points are f of c and f of c plus delta x. Let's connect the 2 points to form our secant line and think about how we would write the slope in general. Well, we know it's the change in y over the change in x, but let's use what I have labeled as opposed to specific numbers to write the slope here. In this case, the change in y values would be f of c plus delta x minus f of c. The change in x is c plus delta x minus c, which is simply delta x. This is where we get to see a connection to what you've been learning about, limits. As delta x gets closer to 0, we get closer to making a tangent line. In other words, as the distance between point D and any other point on this curve gets smaller, we keep sketching those secant lines between those 2 points, and we're going to get closer and closer to making a tangent line at point D. Here's a visual. Notice here the gray point and the red point on the curve. Connecting them creates a secant line. But if I move the red point closer and closer to the gray point to create a short distance between them, when I get close enough, eventually the red point will be the gray point. And therefore, connecting them, we just have a tangent line to that gray point. Ta-da! Back to our connection of limits. Here is formally how we can write the slope for a tangent line at a point. The limit as delta x approaches 0 of the slope of the secant line, which is f of c plus delta x minus f of c all over delta x. You need to know this. Finally, let's do a couple examples. Suppose we want to find the slope of the function 2x plus 3 at the point 2, 1. Well, I hope you realize that this is a linear function, which means the slope is the same at every point because it's a line. And if you recall slope-intercept form y equals mx plus b, you might already be a smarty pants and realize the slope is 2 everywhere. But let's go through the limit process anyways so you can see how to arrive at the answer. The c value in this case is 2. Simply substitute 2 in and we have the limit as delta x approaches 0 of 2 times 2 plus delta x plus 3 minus the quantity 2 times 2 plus 3 all over delta x. When we simplify and evaluate the limit, we just end up with 2. Cool. Let's see an example now of a function that's not linear, and we might not be able to predict the slope as easily. In this example, we want to find the slope of the tangent line to the curve x squared plus 1 at 2 different points. Part A, we're going to find the slope at the point 0, 1. Part B, negative 1, 2. For part A, our c value is 0. Let's substitute 0 in using our limit definition. Simplify this, and evaluating the limit, we get 0. For part B, our c value is negative 1. Let's substitute negative 1 in using our limit definition. You might want to pause the video and try to do it on your own and see what you get. When I substitute negative 1, simplify everything and clean it up, and then evaluate the limit as delta x approaches 0. You'll get negative 2. So, just to get a visual understanding, we all know what the graph of x squared plus 1 looks like. Imagine the tangent line at the point 0, 1. It's a horizontal line. Its slope is 0. Similarly, let's sketch the tangent line at the point negative 1, 2. Yeah, it does indeed appear that the line has a slope of negative 2. So, yay, go us. Hey, we never did answer that opening question. So what does it mean when we say a line is tangent to a point on a curve? We mean the line perpendicular to the radius of the circle at that particular point. The slope of the tangent line at that point is the limit as delta x approaches 0 of the secant line slope. Now to conclude the video, I want you to know that you just learned one of the most fundamental ideas in calculus. The slope of the tangent line, aka the instantaneous rate of change at a point, is also known as the derivative. That's it for today, folks. Until next time, thanks for watching.